Hi everyone, my name is Neha Kardam and in this lecture we are going to learn about counters. So let's get started. So these are the topics which we'll be covering in the lecture. We will learn about overview of counters, characteristics of counters, ripple up counter, ripple up counter with waveforms, ripple down counter, and then self-stopping counter, frequency division using counters, ICs, magnitude comparators, troubleshooting hints, and then we will see the DIY experimental tachometer, which you can basically make the circuit yourself and test it out to see how the counter works. So let's first start with the overview of counters. So counter by definition, it is basically a sequential digital circuit whose output progresses in a predictable repeating pattern. So when we talk about count sequence, then it is basically the specific series of output states through which a counter progresses. And in the counter, we have like a input, which is basically our clock, and then we have outputs follow the defined sequence. Now let's see what are the common tasks of a counter. So you see a list of tasks which a counter can perform. Count up or down, it can increment or decrement count, sequence events, divide frequency, address memories as temporary memory. So almost any complex digital system, it contains several counters, and the very common function of the counter is to count the events or period of time or putting events into sequence. Not so common function of the counter, which you might not know, is that it can divide the frequency, it can address the memory, and it can serve as a memory unit. Okay, so we are going to see some of it in this lecture, how we can utilize the counter into these applications. So let's start with a quiz based on what we covered in the previous slide. So it says a digital counter has a single clock input with many outputs, and the counter follows defined sequence such as this sequence. So is it true or false? So we learned that counter has the application of the counter is to one of the application is to define the sequence. So based on that, this statement is true, so the answer is true. Second, it says several common tasks of a counter are to count up and down or down, divide frequency, or as temporary memory. So this is also true because we learned these are the common tasks which counter can perform. So this is also true. Now next is the characteristics of counters. So we have number of bits, 4 bits, 8 bits, and we can use 32 bits, 64 bits. These can be used in a counter. And then maximum count, 4-bit is equals to 2 to the power 4, which means 4 binary inputs or different combinations we can have in the counter. And if you are using 8-bit, then that means you will have 8 inputs or 8 different combinations of inputs you can have in counter. And then you have and then so what does it mean? So if we talk about like 4-bit, and which means that it can count from 000 00000 to 1111. So it can count in between these two sequence of numbers, and same with this one, it can count in between this. So it can be in the ascending order or descending order, whatever way you want to implement your counter. You can based on the application, you can implement it, and you can use a 4-bit or 8-bit and so on. Now what is the modulus of counter numbers of states? So modulus, if we design a counter, for example, to count from let's take an example of 4-bit 0000 to 1111. We need a device that has 16 different output states. Okay, because if you count from here to 1111, these are all 16 different states. So which means in that sense we can say that the modulus of that kind of counter should be 16. Okay, which means the modulus of a counter is the number of different states the counter must go through to complete its counting cycle. Let's take another example. So if you have mod 6 counter, it means that it is going to count from 0 to 5. And if you have mod 10 counter, then it is going to count from 0 to 9 in decimal. And if you see here a 4-bit counter, so this we already discussed that this is going to count from 0 to 16, 0 to 15, and if you have 8-bit counter, then this is going to count from 0 to 255 for 255 stages. Now what is decade counter? So this decade counter basically counts in decimal digits rather than binary. And then you already know 4-bit counter and 8-bit counters, and they can count in up and down. They can be asynchronous and synchronous counter. So the asynchronous counter, let's discuss this. It is also called ripple counter, and this label means that all the flip-flops they do not trigger at one time in this type of asynchronous counter, and that happens because of the integral proportional delay which occurs in the flip-flop, and that changes the input clock pulse, and therefore it changes the output, which is your Q in the flip-flop, and it can never occur like at the same time, and due to this propagation delay, this is called your asynchronous operation. Whereas in the synchronous counter, this has the advantage over asynchronous counter, because in this one there is no increasing time delay due to all flip-flops they get activated in parallel, and thus the maximum operating frequency of this synchronous counter will be considerably higher than for the equivalent asynchronous counter. And then you have a settable counter. So in this counter, this type of counter, it enables the counters to begin from any value. For example, it can count from let's say from 7 to 14, or 3 to 9. So those type of sequence counting you can have in if you have something application like that, you can use a presettable counter and implement that counting sequence. And then we have a self-stopping counter. So self-stopping counter is designed in such a way that that it will count up till certain number, and then after that it will stop by itself. And in this lecture, we are going to see some of the self-stopping counters, and you will then better understand like how it works. Now let's move on to the quiz. A 4-bit counter will count from 0000 to how much? So if it is a 4-bit, then it's gonna count until 1111. So that's our answer. And then the modulus of a counter is the number of states it will cycle through such a decade. Counter has a modulus of how much? For a decade counter, it is till 10. It can take till 10. So 10 is our answer. And then we have counters can be designed to count up or downward, or devised to be self-stopping. So is it true or false? So we learned about that it can do all of these things. So this is true. And then we have a 4-bit counter which would have modulus of 4 because it is constructed using 4 flip-flops. So is it true or false? It is not necessarily true that if it is If it is a mod 4 counter, then it will be using 4 flip-flops. Like this is not the reason for that, so, and we haven't learned about this in the previous slide, so the answer for this is false. Now let's see our first counter, which is a ripple counter. And you can see a ripple counter, this ripple counter is a 4-bit and it uses 4 flip-flops, and we have used JK flip-flop. And you know that JK flip-flop, it has like 4 states, 4 different states, and but then for counter application, we'll be using the toggle state. It has, if you remember, if you go back to the previous lecture, you will know that it has like preset, it has a set, reset, and then toggle and the hold state. Okay, where it toggles when J and K are 1. So that's what state which we are using in the counters, and that's what you see here. It says all J and K should be equals to 1. And if these two are equals to 1, then your output, which is Q, is going to toggle. So if you have like 0 previously, and if you put like J and K equals to 1, then your next state for the Q is going to be 1. So it will toggle from 0 to 1. So that's one thing which you have to remember, that we use J and K in a toggle state in case of a counter, and then your all clear and presets, they are 1. So you have a preset here and then a clear, they both are equals to 1, or you can say they are tied to logic 1. And then you have outputs which are basically coming out from the from Q. So you can see this, the first Q which you see here basically represents your LSB, which is your lower significant bit, and then so on. This is your second, and this is third bit. It represents coming out from this flip-flop 3, and then the fourth one represents your main significant or most significant bit. Okay, now let's see how it works. So let's read all these points, what it says on the slide. It says PS and clear inputs are inactive when they are tied to 1, and all JK flip-flops in the toggle mode. So we already discussed that. Now let's see what will happen if we provide the first pulse. First pulse, when we provide it here to the clock, then this flip-flop will be activated, right? So when this will be activated, let's assume that previously it was 0. So I'm going back to the previous mode when the output was set to 0, 0, 0. So you see that here everything was 0, and when I provide the pulse and then based on the truth table of JK flip-flop, we know that when J and K are 1, then it's going to toggle. So this is, you can see that the toggle has been shown over here, that it was 0 and now it's 1, and then that output, which is 1, will go into this flip-flop, and that reflection will come in the second pulse. So you can see when you have the second pulse, then what will happen? This has already gone into this second flip-flop, and when it goes there, then it will basically toggle second flip-flop, and that's why you see 1 here, and then the previous one toggle backs to 0. So this is toggled again from 1 to 0, and that's why you see 0 here. And if you see that previously, let's go again. So this 0, 0, 0, 1 represents your 1, and in the second pulse, when your binary output comes out to be 0, 0, 1, 0, what does it represent in binary, in decimal? So in decimal it is 2. So you see how it has counted from 0 to 1 to 2, and then as you go on increasing the pulse, then you will see the change here. Now it is 3, and then as you change the pulse more, provide the clock pulse at the fourth pulse, then what will happen? You got 0 1 0 0, which is your 4. And then like how this is happening, you need to see like how your outputs going into these flip-flops, and based on that they are responding in each stage. And we are going to see the timing waveform also in the next slide. So until now you understood that with each pulse how this binary output is counting up, and it has changed from 0 to 4, and if you provide pulse 5 then it will change to 5. So you can see this is 1s, 2s, 4s and 8s. So if you count, this is your 5 in decimal. And then again in 6 it will be 1 1 0, and in 7 it will be 0 1 1 1. So now on the next clock pulse, which will be 8, all flip-flops will toggle because each will receive a high to low pulse one after another. Was the counter ripple through the counter. So after this state, this is the very special stage when at pulse 7, what is going to happen is all these 3 ones are going to turn into zeros. They will toggle to zeros, whereas this fourth one will toggle to 1. So at this stage all the 4 flip-flops will be you can say energized. You can say they will all toggle together. So let's see, when pulse 8 is provided, you can see that all of these, their output will be toggled, and that's why you got 1 0 0 0. So this 4-bit counter has 16 states and will count from 0 0 0 0 through 1 1 1 1, and then reset back to zeros 0 0 0. The counter has a modulus of 16. So we already know that since it is a 4-bit, so this is going to be modulus, this is going to have the modulus of 16. Now let's see ripple counter with a waveform. So this is the same circuit which we have seen previously. Now the addition is to see the timing circuit or timing waveform. So let's see what will happen when the first pulse is provided. So this is your clock pulse you see here. Okay, so and you know that previously it was all 0 0 0 0. And when the first pulse is provided, then this JK, when these two are in the toggle condition, which means J and K is equals to 1, then whatever Q was previously is going to toggle. So it has become 1, and that's what you can see here. When the clock pulse is made, then you can see from here this first output, this represents your first output corresponding to first flip-flop, and it is turned on, okay, or you can say it is put at a high state, which is 1. Now let's see what will happen to the second pulse. So we are going to have a second pulse, and until the second pulse is applied, the first flip-flop is going to be at the same binary input, which was 1, and then it will turn down to 0, and that's why you see here 0. But at that second pulse, you see you have 1 going in there, and that's why in the second pulse this will basically toggle. In the first pulse this was not toggling because the clock was just going into this first flip-flop, and corresponding to that you were getting the toggle condition, and rest were receiving at that particular instance was you can say that these were not basically turned on, so they were all off. I'll just go back. Okay, so when the third pulse is provided, then what will happen? So this is your third pulse, and at the third pulse, then your first flip-flop will toggle again from 0 to 1, and then your second flip-flop, which is this, it will stays at 1. So that is what it is happening here. And then when you have pulse 4, then what will happen? This is your pulse 4. Then again from low to high it will go, or your first flip-flop, and then second flip-flop will stays high and it will go low. until fourth flip-flop and fourth pulse, and then your force output. So this force output is this one. So this is one's output, second output, and then force output, and then eight's output. So this force output will be turned on at a fourth pulse, you can see here. Okay, so and then when the fifth pulse is provided, again you have a fifth pulse, and then what will happen after the fifth? At the fifth pulse, your first ones will be remain 0, and then this will remain 0, and then at the end of this pulse, it will be turned on from 0 to 1, and that's what you see here. And this is still 0, and that's why you see here 0, and you see here this is turned on, so that's why you see here 1. And then the 8's output has not been mentioned here, but we can see here it is 0. So if we even represent it, then it is going to be straight line, which is at a lower state, okay, which is 0. So you see how this is changing, how this output is binary output is changing, how it is counting up for this particular case, and you can see how this timing diagram can be formed from this flip-flop, from this ripple counter. And then if you do not understand at this point like how this is working, then you need to like maybe put up a stage. For example, when first pulse is provided, and then what is the state of this flip-flop, what is the state of this flip-flop, what is the state of this flip-flop, and what is the state of this flip-flop, which means that at that particular first case, when your pulse 1 is provided, then what is your Q, what is this Q, what is this Q, what is this Q, and what is going into this Q in these clocks at that pulse 1. Okay, and when you have pulse 2, then you have to see that where the output is going into this second flip-flop, and what is the behavior of these all flip-flops in the second pulse. And by that way you can understand how these binary outputs has been created. But for now, understand that that's how it works, and this is the timing waveform, and this is counting up from 0 to 15. So flip-flops are triggered on high to low pulse. Okay, and then clock toggles once flip-flop toggles second flip-flop, and second flip-flop toggles fourth flip-flops. So that's what we saw here, that first this was toggled, and then that sent the output as a clock pulse to the second one and toggles that one, and then so on toggles the other next flip-flop. So this was the ripple counter with waveforms. Now let's see the quiz. So after pulse 1, the output of the mod 16 counter will be binary. So we have to see like what is going to be the output after one pulse. So we know that when the one pulse is provided, then this will be turned on, this will toggle. So this is going to be 0, 0, 0, 1. So that's what you have here. And then you have after pulse 2, the output of the mod 16 counter will be what? So after second pulse, we know that the first flip-flop is going to toggle the second one, and this will toggle to the next state. So right now if it is 1, this is toggle to 0, and this 0 will toggle to 1. So we have 0, 0, 1, 0. And then we have after 8 pulse, the output of the mod 16 counter will be. So after 8th pulse, so 8th pulse, we know that it is going to turn, it is going to be set at 8 decimal, which is 1000. So that is going to be our answer. And then after 15 pulse, the output of the mod 16 counter will be, so we are counting from 0 to 15. So at 15 is our last, which means these all going to be turned on, or you can say all of these going to be these all going to be turned on, and they will have 1 1 1 1. So that's what we have here. So this is all about ripple counter, and we will cover the next counters in the next lectures. So this is now for all. Thank you so much for watching.